Welcome back. So our next speaker is Dmitri Efetov, and unfortunately, due to some unexpected traveling related reasons, he's not able to come here in person. Instead, he'll give a talk on through Zoom. So can we start now? Uh, is
Hey, can
okay?
you hear me okay?
Yeah, I think we can hear you.
Okay, all right, thank you. Okay, yeah, so first of all, want to apologize again for the organizers that I had a force majeure yesterday, so I couldn't register for the flight, and then also in the airport, somehow we ran out of time to do all the paperwork. So hopefully next time I can fix this problem. Anyways, thank you very much also for the opportunity to speak nevertheless online today. And basically, since I was given two lectures during this school, I will basically divided the sort of two presentations in the following fashion, where in the beginning I will basically just give a introduction of twisted violet graphene, in particular, sort of the concepts that go into the engineering of the topological flat bands in it, and also present all of the different strongly correlated phases that people have observed in the systems. I will then also talk about the topological heavy fermion model, which is gaining popularity in sort of describing all the different type of phenomena that we observe in the system, including insulating, but also itinerant electron phases. And I will also give a little bit of an outlook of sort of expanding these concepts to novel types of materials. And then I consider this sort of like a broader introduction to the field. And then tomorrow, at the lecture, I will try to give a little bit more of a very recent update where I believe the field is heading into. So in particular, we have devised improved fabrication protocols that are allowing now us to build much more reproducible phase diagrams that are also much less strain in the samples. I will talk about the quantum twisted microscope, where which evolved as sort of a new technique to immediately prepare and sort of measure these twisted heterostructures. And last but not least, I'll talk also about some quantum sensing with the two-dimensional superconducting states formed by these moire materials. Okay, so basically to jump right into, right? So as we know, over the last couple of years, people have managed to sort of assemble these super periodic moire lattices by just twisting two individual two-dimensional materials with one another. And I think this sort of how these devices really look like exemplifies the best as sort of these STM images that people are taking, where you basically can see the topography of such a twisted biolographene device, where you can actually see the underlying single graphene lattice, which is sort of these small honeycomb periodic structures that you see. But on top of that, you can see that really long range, sort of really orders of 100 longer structures can appear, which are these moire supercells. And of course, the main topic of the talk is then how these moire supercells renormalize the band structures, and then also the electronic behavior of these materials. Okay, and I have to say this sort of trick of building heterostructures is of course not entirely new. So really assembling different materials one on top of another has been, of course, been going on for decades. In particular, you can imagine that molecular beam epitaxy was one of the most prominent techniques in this business. And really, while really the control of these molecular beam epitaxy growth is extremely good, it's basically relying really on sprinkling individual atoms on a parent substrate and sort of growing layer by layer these heterostructures. These techniques did not allow you to do is to just really change the crystallographic orientation of the layers. So basically, one had to rely on the fact that really each grown layer inherits the crystallographic orientation of the underlying parent substrate. And therefore, you could really grow only layers one by one in the same crystallographic orientation. And really, these van der Waals materials have opened up this new capability of also rotating the individual layers with one another because we start assembling the crystal, the sort of designer van der Waals crystal, we start assembling it from individual 2D layers, and not from individual atoms, but really from crystals. And therefore, really, we can sort of embed any type of crystallographic orientation that we want. So really, this is a new sort of tuning knob that we have as this free crystallographic orientation of the 2D layers. Okay, so in the case of graphene, to start sort of looking at the details here, in the case of graphene, we basically start with this single layer sheet of graphene, which has a unit cell of only around 0.14 nanometers. It has this hexagonal brilliant zone with Dirac cones in the K and K prime points. And basically, whenever we stack a second layer of graphene on top of this one and start rotating it, we necessarily sort of induce this geometric interference pattern, which is this Moiré superpotential. Okay, and for any given twist angle that we sort of ingrain into the sample, in particular, of course, we're interested in twist angles of around 1 degree, where the Moiré supercell has sort of a lattice constant of around 10 nanometers. So we create again this superpotential through the Moiré, and also because the superpotential also gives us a second periodicity to construct Bloch wave functions. We also basically create a second set of mini brilliant zones, which you can see here. And these mini brilliant zones are basically set up sort of by within the edges of the individual brilliant zones of the top and bottom layer of graphene. And if the Dirac cones of the two layers sort of come very close to one another in K space, they start hybridizing and they start forming sort of a new type of a band structure, which starts to deviate quite dramatically from the band structure, the Dirac band structure originally given by the single layer graphene. Okay, and so basically this problem was originally explored theoretically. This was done by Alan McDonald and Rafi Bistritzer in 2010. And they constructed for this the Bistritzer-McDonald model, which basically allowed for sort of hopping terms between the top and bottom layer, which sort of oscillate with this continuous periodicity of the Moiré superpotential. And so here is a calculation by the also by the Jarillo-Herrero group, which sort of shows how the band structure calculated with the Bistritzer-McDonald model renormalizes when we start twisting the graphene layers. And basically, as you can see, so if we start at 3 degrees, the band structure looks very similar to just single layer graphene. You have these Dirac cones in the K and K prime points, which are basically follow a linear band dispersion. And okay. Right. And so sorry, just trying to, trying to move the video. And as you can see, so if we sort of change the twist angle, the band structure renormalizes dramatically. And at exactly the 1.1, which we call the magic angle, actually a set of ultra flat bands appear, which basically where the dispersion basically goes to 0. And you can also see here from the Bistritzer-McDonald model, if you calculate the velocity in such a band as a function of twist angle, so it really drops dramatically to 0 when you get closer to 1 degree. Okay, so basically, if if we now talk about twisted bilayer graphene, we usually have this flat band system in mind, where really we obtain sort of a set of flat bands close to the charge neutrality point, which have a bandwidth of around 10 millielectron volts. And basically, this is a reduction in bandwidth of almost 1,000. So in single layer graphene, the bandwidth is typically 6 electron volts. So here we could really reduce this bandwidth to around 10 MeV. So it's really a reduction by a factor of 1,000. And then also what's important is that these flat bands are relatively well isolated from any other dispersive bands, meaning that we have, due to strain and corrugations, we have typically these energy gaps of around 20 to 40 MeV before, again, some higher order dispersive bands sort of appear. And this isolation, of course, makes it very suitable to probe these systems of transport, for example, where you really can look at sort of the resistivity and Hall effect really just coming in these flat bands. So, and the second thing is, so basically, okay, so we have flat bands with sort of very small Fermi velocity. But the second thing, which is sort of also a main ingredient in the formation of twisted bilayer graphene bands, is that also these bands are topologically non-trivial. And this really has its origin from the fact that we really create new brilliant zones in the K space, and we create a set of 2 brilliant zones, which are basically separated in K space quite far. So there's really a little interaction between them. But as you can see, so one brilliant zone, the red one here, is purely created from the K and K points in the individual graphene layers. And the other one is purely made out of the K prime points in the individual graphene layers. So that means that really, if you look at sort of the brilliant zone individually, they have sort of net positive helicity or barrier curvature in the individual unit cell brilliant zone, and then in the other one, it's exactly net negative. So meaning that if you would integrate your barrier curvature over these mini brilliant zones, you will actually not cancel the different contribution from the K prime points, but you actually would sort of end up with Chern numbers of 2 or -2 individually. Okay, so this really ingrains sort of this topological property of these bands, where these bands are really inherently topological in nature. And so therefore, we really have now a model system which has all of those ingredients ingrained into them. So first, it has a quenched kinetic energy because the bands are ultra flat and the Fermi velocity is very small. The kinetic interaction energy is not necessarily boosted, even though it can be boosted by the high density of states in such flat bands. But we definitely can easily reach the limit where the interaction energy now is much bigger than the kinetic energy. So this is really the important criteria for Mott insulators, for example. And on top of that, the bands are topological, and therefore really it turns out to be a very interesting system to sort of induce novel quantum phases, but also really just a rich platform to engineer band structures with topology and interaction. Okay, so just to give you now a little bit more experimental overview of these type of twisted bilayer graphene devices. So here on the left, you can see a sort of larger cutout of a STM measurement on such twisted bilayer graphene devices. You can see that there's really over 250 by 250 nanometers, a very sort of homogeneous Moraine interference pattern. And really the individual lattice sites that you see here, they're really not individual atoms. They are these AA lattice sites on the Moraine unit cell. And of course, one can also, on these open surface devices that were assembled for STM, one can also try to do some ARPAs. And this is some ARPAs that we've done with the group of Felix Baumberger, where really ARPAs for close to magic angle devices can also really reveal the existence of these flat bands. Of course, things are a little bit blurred as the resolution is um, not is basically hitting the limit of what one can resolve in twisted violet graphene energy scales, but you can clearly see a flat band appearing close to charge neutrality. You see these energy gaps that are separated to higher order bands, and you can also see sort of the foldings of the Fermi surface in the system. Okay, so the some of the most prominent experiments, however, to really, especially in the beginning, to really reveal all of those different phases have been done in particularly in transport, but of course also STM and local probe techniques proven extremely powerful techniques to study these materials. But I'll focus on transport now because it's closer to what we do in our group. And basically, the other thing again in these materials, which is really nice, is that you can integrate them in these van der Waals heterostructures and sort of apply all the different tricks we learned over the years to do in this field. And the typical devices are then encapsulated in hexagonal boron nitride layers. Those are just insulating spacers that improve the quality of the TBG. We can add, for example, graphite layers underneath it, which sort of also help screen a disorder, but that they also can be used just as metal layers on which we can apply a voltage and capacitively charge electrons into the TBG. So we can use it as a gate electrode. And of course, we can also shape the devices in any type of configuration that we like. And really, with this, in particular, this gated geometry allows us to completely empty and completely fill the flat bands and really measure entire phase diagrams as a function of the Fermi energy in the system. Okay, and so basically here is some sort of phase diagrams from our group that we now believe are highly reproducible data, and I will actually tomorrow I will show much more about sort of these type of phase diagrams that we started assembling recently, and you can see here sort of on the top you can see a typical phase diagram for longitudinal resistance as a function of temperature and filling, and on the bottom you can see sort of similar longitudinal resistance, but now as a function of magnetic field and filling. And just to also mention this from the beginning, so right, I mean, filling factor that is basically something which is proportional to the carrier concentration that we induce into the flat bands, and it really just corresponds to how many number of electrons or holes we load in the individual unit cell. So basically, when we sort of load 1, 2, 3, 4 electrons into the conduction band, we basically fill up entirely the conduction band, and we hit the energy gap in the band structure that I showed before. And same thing for holes, where we basically empty it out completely and hit the band insulator. So basically, at sort of filling factor 4 and -4 in such a phase diagram, we have band insulators, so trivial insulating states, which is exemplified by this dark red color scale in the resistance. And then you can see that in between, sort of in the flat band region of the measurement here, we see sort of that the resistance changes dramatically. And in particular, we can see that the resistance at integer fillings often turns to be quite insulating. And we can basically see in particular that at filling factor 2, at filling factor 3, and at filling factor -2, there are really strong insulating states appearing at exactly integer fillings of these values. And those states are understood as correlated insulating states. However, of course, I will talk more about the ongoing debate what type of ground state these states are really really existing. And then close to sort of these correlated insulating states, we see superconducting regions where resistance drops to perfectly zero, where we can see sort of the quenching of the superconductivity by applying a perpendicular magnetic field. And also we can make sort of Josephson junction devices by making sort of barriers in the superconductors to observe Fraunhofer interference patterns and so on. And typically the strongest superconductor that is most reproducible between all the devices is sitting here at -2 to -3. Usually this superconductor has a TC of around 3 Kelvin. So this is the strongest superconductor. Once in a while, we see also superconducting regions in other sort of locations, but this is really by far the most sort of robust superconducting state that we have here. Then also surrounding this sort of metallic region of the TBG, so especially at elevated temperatures, we see a strange metal phase, which we call this way because it has a resistivity that is linear in temperature down to really even millikelvin temperature scales with an extremely high slope and basically which is Planckian limited. And this strange metal phase really surrounds a lot of these sort of phases around filling factor -2, where also sort of the superconducting phase is located. And closer to the sort of integer fill, closer to the band edges, we actually lose this strange metal behavior, and we sort of see a T-square behavior close to the band edges and closer to the charge neutrality point. So, okay, so this is about the sort of insulating and metallic phases, but then there's really also strong signatures of these topological phases in the system. So in particular, if you look at the magnetic field dependent phase diagram here, where in high magnetic field, you can see that really a rich sequence of Landau fan-like features appear. People have worked out really extremely robust Chern insulators, which follow a sequence of corresponding from which filling factor they originate from. So you can see these features here highlighted in these orange lines. So they have Chern factors of 4 if they come from the charge neutrality point, Chern numbers of 3 if they come from filling factor 1, and so on. And those are understood as Chern insulators in the system, which have also quite larger gaps than, for example, traditional Landau levels in magnetic field. Okay, and another sort of clear sort of evidence of these Chern insulators, many groups have seen also at zero magnetic fields. So in particular, in our group, we've seen it several times at filling factor 1 or filling factor 3, where you can see this Chern insulators actually persisting down to zero magnetic fields, where you can see these hysteretic RXY signatures and RXX signatures. And in particular, the groups, for example, of Goldhaber-Gordon and Andrea Young, they have also shown that these phases can be perfectly quantized, even at filling factor 3, if you actually help the system to break the symmetries by aligning with it with hexagonal boron nitride layers. And last but not least, in the sort of more sort of in the thermodynamic domain of the measurements that you have to do, also the Pomeranchuk effect has been observed around filling factor 1, which is basically these not fully formed sort of integer insulators, but basically are metallic states that sort of are thermodynamically not fully stable and sort of get even stronger at high magnetic fields. Okay, so with this sort of, I hope I showed the richness of all those phases. So now I just really wanted to spend 1 or 2 slides to get a little bit more into the details of what we sort of know from these or what sort of the current state of thinking about all those phases that I have just presented. And in particular, so the first sort of thing is that we really observe these strongly correlated insulators at integer filling. And I have to say, so first of all, there is really a hierarchy between which insulators are actually very strong and very well developed, and which insulators fail short of that. So, and in particular, as you look at this graph here, you will see that these correlated insulators at filling factor 2, 3, and -2, they're typically really well developed. So really in transport, we observe activated behavior. In STM, people observe really large gaps in these insulators, so 2, 3, and -2. However, as you can see, at -1, here at -3, at +1, these insulators are not fully formed. Okay, so and this is still an ongoing sort of debate, is what exactly is the difference between a filling factor 1 and a filling factor 2 state. Why consistently in transport experiments, filling factor 2 is really strong, and filling factor 1 is, for example, usually almost absent in terms of an insulator. So of course there is this sort of resistance peak, but it's really not gapped at all. Okay, and so basically, what is I think I will show in a second the different type of ground states that people are sort of debating right now, but really what we understand is that really at high temperatures we have these non-symmetry broken sort of mod-like states where really we basically have already the onset of localization physics, where the electrons really try to localize on the individual lattice sites, which again gives a rise to these resistance peaks. However, it seems that the interaction energies probably are not large enough to really perform some sort of ordering. And the ordering really happens only at the said strongly interacting states like 2, 3, and -2, but they somehow do not form at lower temperatures at -3, -1, and 1. So basically, I think so it's fair to say that really what we sort of understand about these states is that at high temperatures we have sort of a generalized non-symmetry broken like states, and really at lower temperatures only some of them really begin to order, and with the ordering sort of they start breaking the spin and Valley symmetries. And for example, some of the sort of states that people are debating right now are IVC states, IKS states, and so on. Okay, another sort of very important sort of aspects to start building now and understanding the ground states that we are sort of have to construct our states from is really to sort of start building them up from the main ingredients and the main orbitals that we have at hand here. And here some clue is coming from really the different flavors that we have in the system. And of course, dealing with twisted bilayer graphene, we basically can construct our wave functions from the 3 different quantum numbers that we have, which are spin. So we can have spin up and spin down. We can have valley, K and K prime. And of course, we can also have sublattice A and B. And sort of because, as I mentioned before, we have these mini Brillouin zones, which sort of with particular Chern numbers, one can really construct the different orbitals from sort of this sets of wave functions that we have here, right? So basically, it turns out that for each type of combination of the quantum numbers, our Chern band will have either Chern number -1 and 1, or 1, where in particular sort of those 4 at the top have a Chern number -1. Those 4 at the bottom have a Chern number of +1. So in principle, when we start now thinking of what are the potential possible ground states, we can sort of start building our ground states from these orbitals. Okay, and so here really, as I mentioned, one big clue came from the transport and STM measurements, which revealed really the individual states that we can construct out of these topological orbitals. And this really the clue came, for example, from transport, where many groups have shown these type of results. But if you look at sort of these sequence of Chern insulators in magnetic field, you will see that in transport, you can see a very rich sequence of these Chern insulators originating from the different integer fillings, where from filling factor 0, we can get basically defined by the Schrader formula, we can get this Chern insulator with a filling factor of 4. Again, we can extract the Chern number from the slope in the magnetic field, but we can also, of course, just measure RXY or sigma XY and look at the quantization of the plateaus in this region. So they all are matching up. And basically, we can basically identify that somehow from filling factor 0, we typically get a Chern insulator of 4. Originating from filling factor 1, we get a Chern insulator of 3. Filling factor 2, it's 2. And then from filling factor 3, it's a 1. So bottom line is there is a hierarchy of Chern insulators corresponding to the integer fillings they originate from. And this is already a big clue in sort of trying to understand what type of ground states are possible in the system. Another clue is really that some of these states, as I mentioned earlier, can be really traced to zero of magnetic fields, right? So where they can exist really as zero field Chern insulators down to zero field. And you can see it here. So for example, this Chern insulator here, which had a Chern number of 3 in high magnetic field, it somehow sort of progresses down almost to zero magnetic field, where it switches to a Chern number of actually 1. So basically, from filling factor 1, we were able to really resolve close to zero magnetic field, a Chern number of 1 or -1, and then it would sort of undergo a transition to a Chern number of +3 at high magnetic fields. Okay, so basically, what this leads to is sort of what has been done sort of by many theory groups a couple of years ago, in particular in sort of under Bernavik, Oskar Wafek, but also the groups at Harvard and MIT. They basically were able to sort of take these orbitals that I was discussing before and really construct a sort of the potential ground state that one can build up in the system here. Okay, and so in particular, it turns out that at large magnetic fields, most of the time, the system tips over into a very stable valley polarized state, right? So basically, valley polarized, meaning that really the K and K prime quantum numbers are basically filled differently below the Fermi energy, where really the occupancy can sort of tip over and prefer K prime. And this type of valley polarized state is then the one which at high magnetic fields really prevails all of the time. Okay, and basically in the papers that were published at the time, there is also a very sort of logical argument why magnetic fields tend to help polarize the system in these valley polarized states. And so as you can see here, so because we're sort of constructing our ground states from these sort of orbitals with K spin and sublattice, we can really show that the valley polarized states that originate from the different integer filling Fermi surfaces, they have to have basically the corresponding Chern numbers that I have shown you before, right? So basically, if you sort of start from the charge neutrality point, you naturally construct a valley polarized state which has a Chern number of 4. If you start from filling factor 1, you naturally construct a valley polarized state which has a Chern number of 3, and so on. So really, this experimentally observed sequence of high field Chern insulators seems to align really well with sort of the notion of these valley polarized states. However, as you can see, sort of while high magnetic field really helps sort of polarize the systems into these valley polarized states, close to zero energy or zero magnetic field, things actually become much more complicated and much more messy. Also, it turns out that really the different proposed states, they are very, very close in energy. So they're almost degenerate. All those different scenarios that people are proposing are very close in energy, very degenerate, very much dependent on the details of the devices. So strain really matters a lot and can tip the balance between one state or the other into one direction. But generally, I would say so. But generally, a lot of the discussions about what are the integer filling states here revolves around sort of intervalley coherent states, so-called IVC states, IKS states. The Kekulé spiral, I think, was the most sort of discussed about in line of the STM work, which came out of the Yazdani or the Steban-Nash-Berger group. And really, some of sort of this also leads a little bit the way in terms of really understanding why certain integer fillings are very well pronounced and are gapped. For example, as I said, 2, 3, and -2 are gapped states. However, some of the other integer fillings are not gapped at all, and really don't form sort of don't really gap out at even at the lowest temperatures. Okay. So then now that I covered sort of the integer fillings, so let me move on and mention a few words about the superconducting states. So the sort of original phase diagram that has been worked out by Pablo Carril Herrero now 8 years ago already showed that there's really, if you look at in the details of the superconducting phases, there's already this notion of dome-shaped superconductors. So really, the superconductors have these dome shapes with a TC again around a few Kelvin, which are directly flanking the Mott insulating states at integer fillings. And this, of course, from the beginning, sort of shaped the notion that, or shaped the sort of the analogy that the phase diagram looks surprisingly similar to the phase diagrams of other strongly correlated superconducting systems, such as the cuprates, such as the heavy fermion compounds, and so on. And really, this sort of proximity of superconducting evolving close to the Mott insulator, which upon doping then becomes superconducting, is quite appealing. However, beyond sort of these sort of similarities, really, if one looks at more concrete the numbers, for example, if one sort of tries to integrate the TBG into the Uemura plot, which sort of compares the critical superconducting temperature and the Fermi temperature between different compounds, it turns out that really twisted bilayer graphene has also an extremely high TC versus TF ratio. Or in other words, while TC is kind of reasonably high, it's a few Kelvin high, the Fermi temperature is extremely low in the system, because we deal here with a semi-metal with a Fermi energy which is very, very close to zero, which is very, very small compared to traditionally to metals. So the TF and the carrier concentration of the electrons that make up the superconducting state is extremely low. So therefore, really, if you look at the TC versus TF ratio, TBG is really only comparable to other unconventional superconductors, again, such as cuprates or heavy fermion compounds, and so on. In general, if you also look at the carrier concentration, TBG has by far the lowest electron concentration that sort of makes up the superconducting state. And again, so here are just a couple of characteristics. So again, TC in the system is around 1 Kelvin. So we can again have a critical temperature of around 100 millitesla in the system, also not too high. The critical current is actually quite low in the system. It's only in the orders of 10 nanoamp, again, for the type of device sizes that we have. And if you sort of try to extract the coherence length just by using Ginzburg-Landau theory on the sort of magnetic extinction of the superconducting state, you get a coherence length of around 50 nanometers. And this coherence length, in principle, is enough to, for example, make Josephson junction devices in the system to really measure also the phase-sensitive transport in these superconductors. And really, there's like a really large number of work already, which sort of in detail studied these Fraunhofer interference patterns. And the one I show you here is just one of the very first, but there are really much more detailed studies about the Fraunhofer interference pattern in these systems. Okay, so and now just a couple of words of course, this field has been now time to probe the nature of the superconductor. Of course, one of the most sort of sought after tests were really to test the pairing symmetry of these superconductors. And there was a large number of works by now. So for example, what I want to highlight is that there were several STM studies, again, by the Yazdani and Nachberger group a couple of years ago, which really were able to observe or reveal this sort of what they thought is the superconducting gaps. And they were basically were able to sort of fit them with different sort of models from sort of S-wave type superconductivity or with different nodal type of superconductivity scenarios. So typically these gaps usually were showing up in a V shape, which of course could be also coming from more disordered superconductors. But if you read these papers, they really did a lot of careful studies to really work out that really nodal superconductivity seemed to be the best fit they could potentially find. And I want to also mention that meanwhile, last year, Pablo Jalero Guerrero's group in particular, they also performed tunneling spectroscopy studies on twisted trilayer graphene devices, where they actually also in more detail were able to work out the gapped structures here. And they also convinced themselves that it's the best fit came from a nodal superconductivity. Okay, so the other sort of really big sort of indication that led to this type of conclusion that nodal superconductivity is a real option here comes from, for example, from last year's studies by the Philip Kim group and by the Will Oliver group, which looked at the superfluid stiffness or superfluid stiffness measurements as a function of temperature. And basically what they were able to show is that really if you measure superfluid stiffness as a function of temperatures from the get-go, basically from the lowest temperatures they were able to measure it, the superfluid stiffness was not scaling as you would expect from an S-wave superconductor as sort of just constant, close to zero temperatures, but it really had this linear drop-off. So really, that is also something which is much more in line with a nodal scenario rather than a S-wave scenario. And also, last but not least, our group did some thermal conductivity studies in TBG superconducting state, where also we were able to show that the dependence of the thermal conductivity as a function of temperature was rather following some power law dependence than a really sharp sort of gapped type of scenario, which again could hint towards a nodal type of superconductor. Okay, and so I think this list is not full, but I'm aware that this year also some further work will sort of is on the way that also supports this type of scenario. Okay, and last but not least, sort of just to summarize sort of the discussion about these different phases, I want to really also show the sort of the linear R versus T data that has been observed sort of in between the correlated insulators in the metallic regions of twisted bilayer graphene. So here you can see sort of data from our group where we measured R versus T in sort of a broad range of doping. So each line corresponds to different dopings. And in particular, as you can see here, close to the sort of close to the center of the bands, these curves were quite linear. Okay, and however, if you were transitioning to closer to the band edges, you were recovering rather a power law dependence of this R versus T. Okay, and so you can, of course, analyze this in more detail if you sort of put it on a log scale. And in particular, we were also interested to look at sort of the lowest possible temperatures that we could reach in our measurement. And really, for many of those curves, specifically in the center of the band, we were able to trace this linear resistivity down from like tenths of millikelvin up to 30 Kelvin. Okay, and where the slope also really consistently would remain the same. And the slope in general is rather large, really reaching values of something like 500 Kelvin, 500 ohms per Kelvin in this case. Okay, so furthermore, we also sort of from Shubnikov-de-Haas oscillations, we were able to extract the effective mass of these electrons in the metallic states. And we were really also able to show that the scattering times that we were extracting from the Drude model here also somehow were in line with the resistivity values and the slopes in the resistivity that we have obtained, sort of hinting towards a potential Planckian scattering rate that sort of defines the resistance values that we observe here. Okay, and last but not least, also the sort of superconducting state that was sort of kind of encompassed by this sort of larger strange metal region, where by sort of killing the superconductor with a small magnetic field, we also could recover this strange metal phase in these devices. Okay, so with this, I sort of gave a little bit the overview of the different phases in twisted bilayer graphene. So now I just wanted to discuss briefly. I think I have still 15 minutes. At least that's what my stopper says. So I wanted to discuss sort of the framework over which it's popular to think about all this rich phenomenology currently. And so basically, from what I have discussed right now, really, there's two types of phenomena that I can sort of generally separate out. So one type of phenomena deals with itinerant electrons. So we observe, again, metallicity, we observe superconductivity, we observe topological phases in the system. So broadly speaking, those are phases, all phases that have to do with itinerant electrons. At the same time, also there's a lot of sort of discussion about localized electrons. We have these correlated insulators that are forming at the lattice sites. Again, a Pomeranchuk effect, for example, observed excess entropy, and so on. So there's also those two aspects. So we have itinerant electrons and we have the conduction, the localized electrons. And one sort of model that had gained a lot of attention over the last couple of years, and I think which is also used quite broadly now by many theorists, is the topological heavy fermion model, which basically allows us to think about those two type of effects in the same theoretical framework. And what this technique, which was introduced first by Gita Song and Andrei Bernovic in 2022, it basically sort of builds up on the Bistritzer-McDonald model. And basically where in the Bistritzer-McDonald, you can already see that different band regions have different sort of Fermi velocities and have different flatness of the bands. In particular, in the Bistritzer-McDonald models, you can find that at the gamma point here, you have actually some curvature in the bands. So the bands are not so flat as one would wish. So really here, if you look at sort of the electron mass, you would find that the electrons are light. However, as you can see, so closer to the M and K points, these bands flatten out dramatically. And if you look at the mass in these regions, it would be a large mass, and these electrons really would be tending to localize much more. And so what Gida and Andre did, they basically performed a very nice basis transformation for the states here, where they were effectively able to separate the localized, sort of the heavy electrons from the light electrons, and sort of translate this into that model. Okay, and so basically the main sort of ingredient in this model is really, or the main sort of picture in which this model works is really in the sort of coexistence of localized F electrons, which tend to sit on the lattice sites, and those are also the ones which eventually tend to like to order and strongly interact with one another. And you have also nearly free electrons, which are the sort of, you can think of them as C electrons, which are sort of also existent in the systems, which can interact strongly with the F electrons and can hybridize with them. And these C electrons in general are topological also in nature. Okay, so, and I think one of the strengths of this technique is that you can actually apply also larger sort of calculational methods to it. And for example, you can directly take this model and perform DMFT calculations to obtain spectral functions of the exact ground states that we're after. And just to give you like one idea before I get into more detail. So this is, for example, I think this was some early on. So I think this maybe has to be updated by now, but this maybe captures, for the sake of my talk, captures the main sort of scenarios here. So for example, you can calculate for filling factor 0 a KIVC state from this model, which would have this type of spectral function, where, as you can see, sort of this type of state would be a gapped state, where the lowest lying excitations in the electron hole bands are actually C electrons. So they're exemplified by these sort of curved bands. And however, at larger energies, you will start having these localized F bands, which are basically this dark blue color. However, for example, if you repeat this type of calculation for filling factor 1 or filling factor 2, you will find that there is now a strong asymmetry between electron and hole excitations, where these symmetry at filling factor 0 is really gone. Now here you have a sort of, on the electron excitations, you hit very quickly these conductive electrons, whereas if you go to the valence band, then you will actually hit the F electrons first. So there's really a huge electron hole asymmetry in a spectral function like that. And one other thing that I think is also important to mention here, because we perform DMFT calculations, what the MIFT gives us directly is not just the energy dispersion of these spectral functions, and also gives us the broadening and lifetime of the quasi-particles that are involved here. So as you can see, sort of this blurring here of these bands, this is really due to sort of the quasi-particle lifetime that is extremely short-lived for the F electrons in particular. Okay, so now just maybe in the last 2 minutes, just wanted to highlight one experiment that we performed to really try to make sense of these spectral functions that were obtained from the topological heavy fermion model. So I will rush a little bit through it because I'm short of time now. But basically, we performed Seebeck measurements, which are these which we performed in a non-traditional way. This is really from optoelectronic measurements that basically give us the photothermal electric effect. And really, we wanted to really see measure the Seebeck effect in the system, because the Seebeck effect is really sensitive to the majority of the carriers. So it really can give us sort of information about electron and holes in a separate way. It can give us information about the mobilities and the lifetimes also of the different excitations of electron and hole type. Okay, and so basically, long story short, and I will make it short now, is that really what we have seen in our Seebeck measurements is that the filling factor 0 states, as I have just presented the spectral functions thereof, they really are highlighted by this sort of S sign changing behavior, which is symmetric on the electron and hole sides. This is exactly what we sort of would obtain from single layer graphene if we would move from the electron to hole sides of the Dirac cone. And really, this sort of behavior really highlights well that electrons give you a negative Seebeck effect, holes give you a positive Seebeck effect. And the symmetry between the two sides really exemplifies that the transport characteristics, so meaning the lifetime and curvature and so on of the band are very, very similar. Okay, so it would be really well compared to single layer graphene. However, in contrast, we have observed that at the correlated insulators, for example, at the gaps that are formed at filling factor 1 and 2, we see very asymmetric Seebeck effect, which is first of all, it's very electron hole asymmetric, but also to the extent that also the hole side of the spectrum here really remains negative even for hole-like excitations. So even hole-like excitations, the Seebeck coefficient gives you an electron-like behavior. And basically, we were able to sort of analyze this type of effect by assuming sort of key ingredients such as mass and lifetime asymmetry between the electron and hole bands. And what we found is really that indeed, so a mass asymmetry between electron and hole bands would already give us such a symmetry. However, the symmetry would never sort of completely quenched the whole contribution. So therefore, this quenching of this contribution we were able only to achieve if we also introduced some whole lifetime, short lifetime of the heavy bands, which then would sort of quench the transport coefficient of the Seebeck effect and would allow us to really reduce the whole coefficient in this system. And this is again, in terms of sort of ingredients that we have in our measurements, this would be the ingredients that would explain such a coefficient. And I want just to come back here, and this is that really this picture that I have just painted is really in line with these DMFT calculations based on the topological heavy fermion model, where in principle for the different ground states that one can obtain at filling factor 0, most of them are electron hole symmetric, and sort of the transport is dictated by the C electrons. Whereas really, if you sort of look at the different ground states at filling factor 1 and filling factor 2, all of them are electron hole asymmetric. And so basically, if you sort of excite in the hole side, you will have, in the electron side, you will always be dominated by these dispersive C electron bands, which dominate the transport. And if you, and have a long lifetime, and if you go to these hole excitations, you will see that really flat bands with a very low lifetime and sort of with very reduced transport coefficient would sort of give you the transport signatures. Okay, so with this, I'm close to wrapping up. I just want to sort of come to the conclusion here of today's talk. And again, tomorrow I'll go in much more details of what I just discussed. But come to the conclusion today. So basically, all those findings that I have just discussed really position this twisted bilayer graphene and moire materials in general as kind of a new experimental platform of strongly correlated physics. And really, it sort of adds sort of a third type of model system or platform or a model platform to the existing strongly correlated community, right? So before that, basically most strongly correlated physics was studied either in crystals, such as cuprates, such as heavy fermion systems, and so on. However, really the interaction energies and the lattice constants here are much lower. So on a lattice constant of 1 angstrom, of course, you would get much larger interaction energy. So here, really in TBG, we have 2 orders of magnitude larger lattice constant, and therefore also a much lower interaction energy. And the other comparison, of course, could be the optical lattices, which are also these synthetic super lattices that people are sort of making by trapping ions in optical lattices. And here, really, the interaction energies are much lower because the lattice constant is much bigger. So I think with moire materials, we're like in an immediate spot between those systems, and there are certain type of experiments we hope to do in these systems that are otherwise not possible on the other ones. But of course, there's also other limitations that this system brings. So with this, really, I want to also highlight that this type of sort of techniques that I have shown you on twisted bilayer graphene is, of course, not limited to twisted bilayer graphene. So over the years, people have actually extended these sort of twist angle engineering and so on to many other material systems. So in particular, not only can you perform 2 layers of graphene and create flat bands from moire engineering, but you can, of course, do it with 3 layers, 4 layers, and 5 layers. So really, these mirror symmetric materials have emerged and have shown also quite high robustness to superconducting states. Then not only can you sort of twist materials, but you can also lattice mismatch moire materials. So you can take, for example, TMD materials with different lattice constants and create moire superlattice even without any twisting. And I have to say these TMD heterostructures also, of course, have become very prominent in the last couple of years, where really novel phases of matter, such as the fractional Chern insulator, have been discovered. And as of last year, these systems also started to show a robust superconductivity, whereas really a couple of years ago, there was maybe a debate that only graphene-based systems can show superconductivity. Really, since last year, we know that this is a much more general phenomena to the world of twisted twistronics. And last but not least, of course, what I think want to highlight here too is that electrostatic engineering, which comes from the ability to build these heterostructures and to apply displacement fields and so on, is also a very powerful tuning knob where you can even create flat bands without any moire involved. Okay, and last but not least, to give a sort of an outlook, what I find fascinating, so the group of Andre Bernavik recently came out with a database of twisted materials. So they basically performed a search algorithm of the database of topological materials that they had established before. So they went really through tens of thousands of materials and to try to identify the materials which are the most promising and most interesting in order to continue expanding the database of twistable materials. So their database basically involved filters such as, can you exfoliate this material? Can you sort of, is the gap of this material small enough that you can actually apply gating and so on? They screened for literature if those materials have been already extracted in literature. So they all of this went in sort of the search here. Then they identified these thin films that are in particular suitable for superconductivity and so on. They bent them into sort of classified them into hexagonal, square, rectangular lattices, K, gamma, M values. So the study, of course, looked at also all of the different DFT band structures of the materials and so on. So this work is now published and is accessible to everybody. So if you are interested to sort of try out new materials, this database really is already available. And just to give you an idea, so what type of materials are sort of were declared promising in this type of database is, for example, these materials like SNSE2 and zirconium S2, where really people have already grown those materials. Those materials have sort of the right type of band structure. So they have a very sort of simple band structure close to the Fermi energy, which is not too convoluted with other bands. These guys have already calculated sort of how these bands are sort of flattened by the twisting. And so what I think one of the most insightful sort of things here is that they find a really broad twist angle where these flat bands can be created, right? So I think the twist angle where they find flat bands is between 2 and 8 degrees. So basically seems like easy enough to fabricate. One of the first things that actually they also found is that really these materials could potentially have different symmetries, right? So for example, here in SNS2, you see that the valleys are actually occupied in the endpoints. So not in the K points like we are used to in graphene or TMDs, but those are really endpoint materials where the Fermi surface is at the endpoint. Okay, and with this, I'm done. And thanks a lot for your attention.
So due to the time limitation, we might have time for one or two quick questions.
Sure.
Okay.
In the resistance versus temperature curve, there were some data points where the resistance dropped with increasing temperature. How do you explain that?
So just to, you mean this graph, right?
Yes, at very high temperatures.
Yeah. So basically, this is the point which you mean, right?
Yes.
Yeah. So this is around 30 Kelvin. If you look at the band structure of TBG, you remember that it has also these small energy gaps that, and after above these energy gaps, we have dispersive bands again. So if you look at the temperature scale here and compare KBT to the energy gaps, then this is about the same range. So this has been worked out in some paper also by Andrea Young early on, is that this drop in resistance, we understand it as a population of the dispersive bands. So there's a second conduction channel populated with a much higher mobility electrons, which lowers the resistance.
Thank you.
I think we have one more question. This side.
Hi, Dmitri. Thank you so much for an incredible presentation. I'm curious. I mean, I had two questions, but I'm going to keep it to one. I'm curious about this condo analogy. I had a question about the resistivity and whether there's, whether there's like a t squared regime, that you can see, and there's a clear condo-like coherence scale that exists, both in the theory and experiment.
Right,
Whether or
right.
not you see an eventual heavy Fermi liquid type or an analogy to, what you'd expect in a condo model for the heavy Fermi liquid at low enough temperature.
Mm-hmm.
And so related to that, my other question was I remember a lot of discussion in the earlier days of TBG of this fragile topology stuff on the theoretical,
Right.
and how reconcilable is the obstruction to defining local moments in the Wanyi picture and stuff with this kind of these very otherwise very compelling two fluid type proposals. Yeah. Thanks.
Okay, so the first question, sorry, what was the first? The first question was
About a t
about T squared, right? Yeah. So mhm. So I will take the opportunity tomorrow to actually try to look more deeper into this question. So we actually do think we see now some evidence of this condo-like behavior. And also there was just this recent paper by Stevan Nachbergi, who did STM studies on these states and who seemed to see some evidence of a condo peak appearing in the spectra. Okay, so I will try to highlight more of this tomorrow then to really go a little bit in the more advanced questions. And the second question was then about it was more like a theory question about fragile topology somehow, right? If I mean, I have not heard. I was under the understanding that this question was settled and that we now understand that this is robust topology in TBG. I remember there was some discussion about fragile topology early on in the field, but I think since around 2020, I only hear about robust topology here. So right. So this is my state of knowledge in that, but I have not I have not followed the fragile topology too closely.
Okay, thank you so